Okay, so welcome back, everybody. Um, so in yesterday's lecture, we had done everything to set up our separation of variables algorithm. So just to refresh your memory here, this is what it looked like. Okay, so first, the thing that gives the algorithm its name, is we seek a solution that is separated, right? A solution that is of the form function of one of the variables x times function the other variable t. Now, we've assumed that we're doing this, right, for like a 1D PDE, so one spatial dimension. But we'll see later how this approach can be adapted to any number of spatial dimensions. Um, but it's crucial to understand it in this case first, just to make it a little simpler. And so we seek a separated solution, which is of this form, right? Function of x times function of t. And then we note that, oh, well, if this is going to satisfy the PDE in question, this is going to lead to some second order ODEs, typically, that are going to involve those eigenvalue problems that we have these canned eigenfunctions and eigenvalues for, right? That we solved earlier, right? So here, right? This ultimately, all of these are solutions to the eigenvalue problem x double prime plus lambda x equals 0, right? So we had our solutions to this for Dirichlet boundary conditions, for Neumann boundary conditions, and for periodic boundary conditions, right? Mixed boundary conditions we'll do a little later, but those were our main three, right? Okay. So this is going to just plugging this into the PDE and doing a little bit of algebra. We're going to see how this reduces to solving eigenvalue problems. That's going to allow us to find x and t, and the way that that works is that the boundary conditions to the PDE descend to boundary conditions for the associated eigenvalue problems for x, we'll say, for the spatial dimension. Okay, because that's how this works, right? These are boundary conditions, so of course these involve the x and not the t for a PDE that involves a time variable here. So anyway, so I'm going to get exactly one of those eigenvalue problems that I hopefully know the eigenfunctions eigenvalues for. And so that's going to allow me to find x. And then for those eigenvalues that I found in this step, I can then use those to solve the eigenvalue problem for t. I can find t in a similar way. And this gives me infinitely many, countably infinitely many separated solutions of this form. So this u sub n of xt is that eigenfunction x sub n of x times eigenfunction t sub n of t that we found from these two steps. And then I seek, or I hope that since I noticed that any finite linear combination of solutions that look like this solve my PDE and boundary conditions, I hope that this infinite sum of this infinite linear combination of these separated solutions solves my PDE and boundary conditions. And the question as to whether or not I can do this is answered in the affirmative that, if this a sub n is actually chosen to be these Fourier series coefficients that we have seen so far, then this whole process works. So this is where our Fourier series methods come in, right? Both in solving these eigenvalue problems and in solving this question of how to choose these coefficients to make this infinite linear combination work. And the answer, of course, is that for reasonable functions involved here, this is the case. Now, how are these chosen? Well, we'll see, but of course this is going to involve the initial condition function, right? Okay. And so, let's see our first example of this in action. Okay, so we're going to do a bunch of general examples for general initial initial data. The point is, of course, if I were to specify any of these functions, you could complete this computation by explicitly computing the coefficients in question. Okay, so let's start with our first example. So example 1, this is diffusion equation with homogeneous Dirichlet boundary condition, right? So diffusion equation with homogeneous Dirichlet boundary conditions. So what does that look like in one spatial dimension? So I have the equation u sub t is equal to alpha u sub xx. We seek a solution on some, right, we're thinking of our region as like a metal bar. So this is x between 0 and L, t greater than 0. All right, here's my PDE. All right, just remind us, this is the PDE. I have boundary conditions. These are going to be homogeneous Dirichlet in this example. So this is u of 0 t is equal to the same as u of L t. And both of these are 0, and that's for t positive. These are my BCs, right? And then my initial condition is some function phi, where x is somewhere in that finite interval 0 to L. This is my initial condition. So this is an IVP, BVP, BVP, IVP. This is this type of equation that in the diffusion case we talked about it a little bit more. In the for the wave equation, right, we saw that this was actually a really complicated, this massively complicated what was going on. For the diffusion equation, this also complicated things, and we basically didn't deal with this directly when we first talked about it. We just kind of analyzed long-term behavior, right? So now's our chance that if we're actually going to be able to use separation of variables here to show what the solution to something like this looks like, then we can ask ourselves if that solution then agrees with our previous our previous thoughts on what the long-term or steady-state solution should look like. And so we'll ask all those questions when we get to them. Okay, so recall the physical interpretation we had of all of this, right? Thinking about this as like a bar here. This is saying that you know, at the end, right? I have you know, I thought about these being inserted into like a very large room, right? A very large room that had constant temperature, right? So I actually did the case of inhomogeneous Dirichlet boundary conditions when we talked about this before. Anyway, so recall the physical interpretation of this heat equation. So let's follow our algorithm, right? Our algorithm says what? We look for separated solution to this PDE. Okay. So our step 1, right? So step 1, I am going to seek solutions to PDE plus boundary condition of the form u of xt is x of x, t of t. Right. Well, if this is going to solve the PDE, then just plugging this in directly gives me what? It would give me x of x times t prime of t, right? So the partial of t becomes a full derivative for this function that only depends on t. And that is equal to the constant alpha times x double prime of x times t of t. Again, these partial derivatives with respect to x become full derivatives of this function x with respect to x. Okay, and just like I did yesterday to kind of give you some motivation for what it is we're doing, we want to put everything involving each of the variables on one side. I'm going to move the alpha with the t's. So this is going to be t prime of t divided by alpha t. So I'm going to divide through by alpha t. And that is equal to x double prime x over x of x. And as I told you previously, for a variety of reasons, to reduce the overall number of signs or something, it's better to adopt the convention where we write these as minus these objects instead. Okay, which of course we can do. Now, I make the key observation here, right? So note, left-hand side is function of t. Right-hand side is function of x. This equation says that these two things must be equal, right? This equality has to hold for all x and for all t. So if this equality holds for all x and t, if this is going to solve this PDE, then what does that mean? It means that these two things actually have to be constant. Right, so these things actually have to be constant. So what it means is that therefore minus t prime of t over alpha t of t is equal to lambda, which is equal to minus x double prime of x over x of x, where lambda is a constant. Now, this expression, considering the left-hand side and the right-hand side separately, leads to two different eigenvalue problems, right? Let me go ahead and label my full PDE like star. Okay, so this leads to two eigenvalue problems. So it leads to the eigenvalue problem. Let's just look here. So now let's consider this by itself. Then, like, multiplying through by x, right? And adding these things, what do I get? I get x double prime plus lambda x is equal to 0. Okay, so leads to two eigenvalue problems. One is x double prime plus lambda x is equal to 0. Hey, that's exactly the eigenvalue problem we put so much effort into solving, and we put so much effort into tying it in with all of the Fourier series stuff that we had talked about. Okay, so it leads to this eigenvalue problem, and the other eigenvalue problem it leads to is, again, this is now looking at this part of the equation. This is going to be t prime plus alpha lambda t equals 0. Right? This is going to be t prime plus amdal alpha lambda t is equal to 0. But notice that if we impose the boundary conditions, right? But what about the BCs? Well, let's revisit these. So my boundary conditions were 0. So u is 0 at the ends of this interval. So u is 0 at x equals 0 and at x equals L. So if my u is of this form, what does this mean? This means that 0 has to be equal to u of 0t, which is x of 0 t of t, and 0 is equal to u of lt, which is x of l t of t. Now, I don't want this t to be a constant 0 function, right? If it was a constant 0 function for all t, I would just get the 0 solution, so that's not what I want, right? Because, of course, the solution I'm seeking looks like this. So if t is 0 for all t, then this is just the 0 solution. So I'm not interested in that. Okay, that's not gonna work. So then what has to be the case? Well, what has to be the case is that these things are 0. And so I get eigenvalue problems where this, right, for associated to this, I have boundary conditions x of 0 equals x of L equals 0, which exactly puts me in this case of, oh, now these are Dirichlet, right, homogeneous Dirichlet boundary conditions for this eigenvalue problem. These are an example of what we called symmetric boundary conditions for this eigenvalue problem, which means that we exactly know what the solution to this is, right? And so what this means is that, so why is this important? Because we've already solved this. Right? We've already solved this thing. In fact, let's look at our list. Well, what happens when I have the following eigenvalue problem, x double prime plus lambda x equals 0, with homogeneous Dirichlet boundary conditions, which is exactly what I have here. What are the eigenfunctions and eigenvalues they correspond to? Well, here, right? And so there are countably many many eigenvalues and eigenfunctions here. Given by exactly this list. Let's just write them out. So the x sub n's are sine m pi x over L. Of course, if this was completely general, this would be some constant times sine of m pi x over L. And the eigenvalues are n squared pi squared over L squared. And so my eigenvalues are n pi L all squared. And my eigenfunctions are like some constant times sine of n pi x over L. Okay, and this is for n 1, 2, 3, and so on. Okay. Now, for now, take c equals 1. We'll see why later. As you might expect when it comes to these sorts of problems, a lot of times this is just hinting at the fact that that constant can be absorbed in another constant that comes later on. So there's no reason leaving that as constant. In fact, when we wrote out our solutions, we didn't even include it here, right? And I made a statement about, for eigenfunctions, not caring about like a constant multiplying it. This is analogous to the statement, if you recall from linear algebra, when you have an eigenvector, eigenvectors are not unique in the sense that they are only defined for eigenvalue up to scalar multiplication, for instance, or the eigenvalues, or I should say eigenvectors, like if you, I should say the simpler thing, if you take an eigenvector and you scale it by a scalar, it's still an eigenvector for the same eigenvalue. And you can prove that directly from the eigenvalue definition, right? The equation that defines an eigenpair lambda v. If you multiply v by some scalar c, then you can prove that cv is also an eigenvector for lambda. So it doesn't change it. All right. So then we have solved this eigenproblem, right? I have countably many eigenvalues lambda sub n and associated eigenfunctions. Okay. Now, what about this one? So now, onward to this one. So let's go back to my algorithm. So I look for separated solution. That allows me to write eigenvalue problems for x and t. There they are, right? These are ODE problems that hopefully I either know how to solve or I've solved already in this case. Okay, so I've gotten to where I solved the eigenvalue problem for x. It's something we already did. Yep, we're good there. So now I want to solve the eigenproblem for t using the lambda sub n eigenvalues found in the previous step. So I found these lambda sub n eigenvalues in my solution to the eigenvalue problem for x. Now I want to use those particular eigenvalues to solve for t, right, from this eigenproblem. Okay. And so this means that I'm looking for, so now I want to solve t prime plus alpha lambda sub n t equals 0, i.e. t prime plus alpha times n pi over L squared t is equal to 0. This is linear constant coefficient. This is about as easy as it gets from ODE, right? This is basically something you do on either day 1 or day 2 of ODE. If you don't believe me, remember, this is just a constant, right? Doesn't matter how scary that looks. So this is t prime is equal to like minus alpha n pi over L squared times t. So I seek an unknown function t such that its derivative is this constant times itself. Well, we know exactly what kind of function that is. So the solution for a particular n is the following. It is just some constant c times the exponential function raised exactly to this constant, right? So this is minus alpha n pi over L squared t. Right? Where c is some constant. Okay, and if you don't believe that this satisfies this ODE, just check, of course, take a first derivative and see if it's equal to that constant times itself. Yes, of course it is, right? Okay, again, take c equal to 1. We'll see why this is. Okay. All right, so then what have we done? We have found our eigenfunctions x sub n. We have found our eigenfunctions t sub n. You might say, wait, that's, in the eigenvalue problem doesn't have to look like this. No, this is another example of an eigenvalue problem. It's just one that's very simple. Right? It's a simpler type of one. Okay. And so we get these two eigenfunction solutions. And so remember, our original goal was seeking solution to the PDE and boundary conditions that look like this. So then we note that for each n, u sub n of xt defined by x sub n of x and t sub n of t. solves the PDE plus boundary conditions? Let's actually write this out just for emphasis here. U sub n of xt is what here in this case? X sub n is sine n pi x over L. This is sine of n pi x over L times t sub n, which we just found is e to the minus alpha times n pi over L squared t. So we'll write it like this. This is e to the minus n squared pi squared alpha t over L. Okay. So this is my solution for each n that solves the PDE plus BCs. Well, if it solves the PDE plus BCs for each n, one thing is I have the superposition principle because this is a linear PDE, right? It's a linear PDE. I have the superposition principle. If I can convince myself that this solves the PDE and BCs, so it solves the PDE because it satisfies these two eigenvalue problems, right? X and t satisfy both of those. And if both of those are satisfied, working backwards here, what does this mean? If both of those are satisfied, well then this relation is satisfied, which means this relation is satisfied, which means that the PDE is solved. Okay, you can also directly check if you don't believe this, right? Take this, right? Compute its t partial, compute its double x partial, and see that u sub t is equal to alpha u sub xx. That will work. To see that it solves the BCs, let's just consider, what are the BCs? At x equals 0 and x equals L, this thing should be 0. Well, I'm multiplying here by sine of n pi x over L, and of course at 0 and at L is exactly when this thing is 0. So, cool. Right? So we're good there. All right. So for each n, this solves the PDE plus boundary conditions. A finite linear combination also is going to solve the PDE plus boundary conditions just by superposition principle. But now I consider something slightly more complicated. Now I consider a solution of the form u of xt is a sum from n equals 1 to infinity of some b sub n coefficients times u sub n. Of course, for a finite sum, this is going to solve the PDE plus boundary condition. So the question is this also going to be true for an infinite sum? And the answer is yes. Okay, and in this case, it absolutely is. If I write out what this is the sum from n equals 1 to infinity of b sub n times sine of n pi x over L times e to the minus n squared pi squared alpha t over L. And I claim that this is my solution for some b sub n that works. Because what have I done so far? I have to be very careful here. I've solved PDE plus boundary conditions. So going back to my original problem, I have found solutions. I've found things that solve this, and I found things that solve this, right? But the question is, can I find something that simultaneously solves the PDE, the boundary conditions, and the initial condition for this generic function phi? So I consider a solution of this form and ask the big question. Can I solve or can I find coefficients b sub n, right, such that this particular u of xt in this form satisfies the initial condition. So this is a big question. What does it mean to satisfy the initial condition? Well, the initial condition, of course, is that u of x0 is equal to phi of x for all x and 0 between 0 and L. That's my initial condition. So, i.e., can I find coefficients b sub n such that phi of x is equal to u of x0, but u of x0, here I'm plugging in 0 for t. When I plug in 0 for t, this is just 1, and so the only thing left in this sum is this. That's familiar, right? So that's familiar. So then this big question can be reworded, right? This big question can be reworded. Thus, I can rephrase this question as follows. Can I find coefficients b sub n such that phi of x is equal to the sum from n equals 1 to infinity of b sub n sine of n pi x over L. But this is exactly the question, right, that we asked on the first day of this stuff. Right? This is literally the first question that we asked, whether or not this was possible. So the answer is yes. And what is the answer? The answer is to use the Fourier sine series and its coefficient. Right? Use the Fourier sine series for phi. i.e., the coefficients that make this work are exactly b sub n, which is 2 over L times the integral from 0 to L of phi of x sine of n pi x over L dx. So, we are done. We are done. We have solved the problem. Now, before you revolt and say, wait, how have we solved the problem? Where's the solution? What is it that's going on? I think it warrants an actual separate page to see how we're done. Okay, so in resolution, maybe I should say, in conclusion, what have we done? The answer is on the next page, which is to say fully what we've done is the following. So piecing all of these together, right? I'm going to revise what it is. This is the thing we're trying to solve. We have, through this process, considered that the solution that we seek is of this form, with coefficients b sub n chosen in a way that the initial condition is satisfied, which means chosen in a way such that the sum from n equals 1 to infinity of b sub n sine of n pi x over L is actually equal to that initial data function phi. And we just concluded that, yes, we can do this if b sub n is the coefficients, if these are the coefficients defined by this Fourier sine series formula for phi. It turns out this question, right, is answered exactly by these, where this question is the first question we ask when we defined Fourier series. It was whether or not I could take a function and write it as a infinite linear combination of sine, for instance. All right. Well, the answer is yes, using the Fourier sine series. Okay, for a wide class of functions, for every type of function that we are going to consider in this class, the answer is yes, and I don't have to worry about issues of convergence or anything like that. So I think it is worth it to nail all of this down on a single page so that we can truly see what we have done. So what have we done? Here's the statement. The solution to the IVP-BVP, which is the diffusion equation with homogeneous Dirichlet boundary conditions, right? So heat equation with homogeneous Dirichlet BCs. This equation is, so heat equation is U sub T equals alpha U sub XX. I have Dirichlet boundary conditions, U of 0. T is equal to U of L of T is equal to 0. And I have an initial condition, U of X0 is equal to phi of X. The domains in question for all of these things, so here X is between 0 and L, so this is a finite interval. T is positive. Here, T is positive. Here, X is between 0 and L. This is the IVP-BVP that we're trying to solve. The solution to this is given by, where did we get this from? We got this from this step. Once we had found our separated solutions for each n, right, each of these eigenfunctions here, then we took the step of considering a solution that was an infinite linear combination of such separated solutions. So like this, okay? And so this is our solution we're claiming, right? It looks like that. So the solution to this is given by u of xt is equal to the sum from n equals 1 to infinity of b sub n sine of n pi x over L e to the minus n squared pi squared alpha t over L. And of course we're not done, because a solution written like this is, it's not complete, because I need to specify what the coefficients are, right? Where b sub n is given by 2 over L times the integral from 0 to L of phi of x sine of n pi x over L dx for n equals 1, 2, and so on. And so this is what we mean by a solution formula. Okay, this is what we mean by a solution formula for our problem. So what have we shown? We have exactly shown this. that solving this IVP BVP yields a solution that is an infinite linear combination, an infinite sum of things of the form b sub n, so coefficient times the product of these eigenfunctions we found, where b sub n are, those are the coefficients coming from the Fourier sine series for phi. And so long as phi is nice enough, all of this works out fine, and this is it. Now you might say to yourself, okay, this is like the general problem, but let's say that you give me explicitly, right, absolutely everything is given here, right? So, maybe like alpha is equal to 5 or something, or alpha is equal to 1, okay? That's not too much of a problem, of course, in this formula. But let's say that phi of x is now a specific function, right? Like phi of x is a specific function, so phi of x is like x squared, right? Phi of x is x squared, phi of x is x cubed, whatever, right? Phi of x is e to the minus x. Whatever this thing is, how does that change? Like, can you just say, oh yeah, the solution is this, and the coefficients are 2 over L times the integral from 0 to L of e to the minus x sine of blah, 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 and that's it? No. So note, in the case you are given an explicit phi of x, say phi of x is equal to 2x, e to the x, right? Something, it doesn't matter, whatever, right? So say that you have a phi that looks like this, right? How do you explicitly solve the PDE? Well, you write u as above. And then you explicitly compute, right, as much as possible, the b sub n's. So for the examples that I'll be giving you, these won't be horrible, so you can actually do these just like we did for various cases, right? So like, for instance, when we chose like phi of x equals 1 or phi of x equals x, we saw some particular examples of how those coefficients turned out, right? And so that's what it means to solve. So this is just clearing up the question of if phi of x is equal to x squared, is it solving it if you just write this and stick in x squared and you're done? No, what I want you to do in that case is I want you to explicitly compute these things. But when I assign these problems, and your next homework will be assigned soon. When I assign these problems, I'll be explicit with what I want you to do here. I'll be explicit that, I want you to actually explicitly compute the coefficients, okay? And so what is so cool about this is that, yeah, it might look kind of strange at first. It might seem kind of overwhelming, but what is so cool is that you've actually solved this problem, and this method of doing it can be shifted around a little bit to solve so many of these problems that we've considered previously that were just kind of unmanageable in the previous ways that we dealt with them, right? Like, so the wave equation is the biggest one because you saw how absolutely horrific the wave equation problem was with if you had a string with 2 fixed ends, right? So 1D wave equation, string with 2 fixed ends. That is like a horrifically complicated. You remember the domain of influence and the domain of dependence. It was this extremely complicated. You had to worry about reflections, and it was not simple to see what was going on. But this is going to allow us a way of just very, very simply writing out these things. Okay, and so that's our first example of how this goes. These will go a little bit faster from now on, because it's important that you see one worked out very slowly like that, as in as much detail as possible, because the flavor of this is very similar for all of these problems where you're using separation of variables. So this is going to have a similar flavor, which keeps it nice. Now, before I'm totally done with that, I want to ask you a question, right? So here I say solution is given by this thing. Let's question whether or not this actually makes sense with what we've previously seen. So question, does this make sense with what we've previously seen? Since, given our previous treatment of the diffusion equation. So what do I mean by this? Like, why would there be a problem here? Well, recall that previously such a U was thought of, or was obtained via a convolution. Right? And our convolution, right, was something, it was like, i.e., U was really some phi, which is either the heat kernel or something similar to the heat kernel, right? In this case, right? It's like phi, and maybe you don't like me calling it phi because the thing I'm about to write is not really the heat kernel, but it's related to the heat kernel, or it's similar to the heat kernel. It was something like this, right? It was like some phi, right? Some fundamental solution convoluted with the initial data, right? So this was fundamental solution in some sense, and this is the initial data, right? And so that was how our solution to the heat equation looked like. Well, you have to question, like, does this look like a convolution? Remember, a convolution is like the integral of phi, and there's some stuff times phi with respect to some s, t, y, whatever, right? Does it look like this? Well, at first glance, you might think that it doesn't. But note, there is an integral showing up here, right? In fact, what happens if I actually just write this integral in here, in this slot, right? So I'm going to take u of xt. I'm going to rewrite it. This is the sum from n equals 1 to infinity of b sub n sine of n pi x over L e to the minus n squared pi squared alpha t over L. And now I'm going to insert the b sub n here. Right? I'm going to insert it right here. So this is the sum from n equals 1 to infinity of the integral, or maybe I should say 2 over L times the integral from 0 to L of phi of x sine of n pi x over L dx. That's here, multiplying sine of n pi x over L e to the minus n squared pi squared alpha t over L. Oh man, look at that. Right? So imagine, like, once you get the hang of this and you've done this a few times, of course, you'll be able to basically from memory just write out, say, the solution in the general case. Say it looks like this, to say homogeneous Dirichlet boundary conditions. And think about how you could impress your friends, right, by writing down a solution formula to a given PDE that looks something like this, right? Yeah, they'll definitely think you're a genius or something, right? That you came up with this just off the top of your head. Being able to explicitly solve PDEs mentally, that is pretty impressive. So yeah, maybe that'll be your next parlor trick that you learn to impress people. Just just casually write out the solutions off the top of your head to such problems. I'm sure lots of people will be interested to hear you rambling about that. So, okay. Well, if I do this, then, let me define, we'll call it big phi of xyt. Yeah, so big phi of xyt. Let's say, okay, what is big phi of xyt? Let's define it to be 2 over L times the sum from n equals 1 to infinity of sine of n pi x over L, sine of n pi y over L, times e to the minus n squared pi squared alpha t over L. So basically this phi is defined in a way that it's everything in this expression except the integral and phi, right? So define your big phi of xyt to be this expression. Then note that the u of xt that we wrote down right here can then be written as what? The integral from 0 to L of big phi of xyt, phi of y, dy. Oh. Okay. So, the phi, this big phi was not just given to us from the sky like the heat kernel was, right? It looks different. Okay, and yet the final form of the expression, right, that the solution takes is actually again one of these convolutions, right? So it is in fact a convolution. In a sense. So it is you're integrating some fundamental quantity times the initial data, right, over the interval in question. Cool. All right. Now, on to Neumann boundary conditions for the heat equation. So now, let's do Neumann BCs for the heat equation. So, the associated IVP BVP is U sub t is equal to alpha U sub xx, where again x is between 0 and L, t is positive. That's my PDE, right? My boundary conditions now are Neumann BCs. We'll say homogeneous Neumann BCs. This makes everything easier. We will do not inhomogeneous cases for all these, and you'll see how we adapt there. But for now, let's just do the homogeneous problem because it turns out we need to be able to solve that for the inhomogeneous case anyway, which is probably not that shocking to you. So the flux at the ends is 0. for all t, or for all t positive, I should say. And u of x0, this initial condition, is generic phi of x on my bar. Okay, so these are the BCs, and this is the initial condition. Okay. Now, separation of variables. Again, has me seeking separated solution. U of xt equals x of x, t of t. Okay, you saw how this yielded eigenvalue problems previously, so let's do that again here, right? So what do I get here? So immediately I get eigenvalue problems that look exactly the same. So I get eigenvalue problems for x and for t, where so for t, similar to before, this is t prime plus alpha lambda t is equal to 0. Now I have Neumann BCs. So the Neumann BCs, these are x partial, so it's only hitting x, so these become full derivatives of x in the separated solution, so these become Neumann BCs for my eigenvalue problem. So there's one eigenvalue problem. Here's my second one. I solved this one first with Neumann BCs, but hey, again, I know how to solve this already. Okay, this comes from list. In fact, again, here's the list that I wrote up yesterday during yesterday's lecture. When I have an eigenvalue problem that looks like this, so x double prime plus lambda x equals 0, and now I have Neumann boundary conditions, which is exactly what I have here. Then the eigenfunctions and eigenvalues are now cosine n pi x over L, and my eigenvalues are the same here. Right, so I have eigenvalues lambda n, which is n pi over L squared, and eigenfunctions. Again, I can make that arbitrary constant on the front 1, so my eigenfunctions here are x sub n of x is cosine n pi x over L. Now, something that's a little different is 0 is an eigenvalue here in this case. And so this is for n equals 0, 1, 2, and so on. Okay. When 0 is an eigenvalue, the associated temporal eigenfunction is going to be a constant, right? And so what we ultimately end up getting, so similar conclusions, so similar computations as before, yield a solution u of xt is 1/2 a naught plus the sum from n equals 1 to infinity of a sub n cosine of n pi x over L. Again, my temporal ODE is going to be solved in the exact same way. So this is e to the minus n pi over L squared times alpha t. So this is e to the minus n squared pi squared alpha t over L. Okay, as usual. And the condition phi of x equals u of x0. Again, when I plug in 0 here, what do I get? When I plug in 0 here, I get the Fourier cosine series for phi. So this condition implies that a sub n should be chosen to be 2 over L times the integral from 0 to L of phi of x cosine of n pi x over L dx, i.e. the Fourier cosine coefficients. And so, again, there's what my solution looks like to this Neumann problem. Notice how quick this was to replicate the previous analysis from the first example we did. Everything essentially works in exactly the same way. The only difference is that my canned eigenfunctions that I wrote down from my list were cosine instead, so that the resulting series, right, is the Fourier cosine series. Okay. Now it's time to check something. Right now it is time to check something. So I want to now check a previous statement that I made about this problem. Now we can verify whether our previous intuition about the steady state or long-term behavior of Neumann, or maybe I should say diffusion equation, or heat equation with homogeneous Neumann BCs. So now we can verify whether our previous intuition about the steady state or long-term behavior of heat equation with homogeneous Neumann BCs is accurate or not, or is accurate. So what is it that we previously said? Recall here the interpretation of this is heat flow in like a 1D, right, bar that I've sat one end at the origin, the other end at some length L. So I have bar of length L. At the ends, my flux, right, is 0. So these are two insulated ends. And at some initial time t, I have a distribution of heat here, right, given by this initial data phi of x. Okay. Now, what was our intuition for how the steady state solution for this should behave? Our idea was that this should go to the average of the initial temperature. That's what we previously said. Right? We previously said that the limit as t goes to positive infinity of u of xt is what we call the steady state solution, and that this should be the average of the initial temp. Right, where by initial temp we mean the temperature prescribed at t equals 0 by this function phi of x. Okay, so that is what we previously said. Well, let's see how this meshes with our formula here. Right, so here's our formula for our solution. Let's take the limit as t goes to infinity of u of xt. What happens here? Well, wait. As t goes to infinity, each of these terms that is multiplied by some eta some minus positive constant times t, that's going to be killed off, right? So everything in this infinite sum is killed off as t goes to infinity. And so clearly all I have is 1/2 a naught, right? But what is a naught, right? A naught is given by this formula for the coefficients. So this is 1/2 times 2 over L times the integral from 0 to L of phi of x cosine of 0 pi x over L dx. The 2's cancel, and I have 1 over L times the integral from 0 to L. Cosine of 0 is 1. So this is phi of x dx. But what is this? This is the average initial temperature. So this is indeed the average initial temperature. So you could say that, maybe if you were skeptical before about whether or not this worked, you'd say this is pretty good evidence that it's spitting out something of use, right? In fact, this works for the same reason it worked in the Dirichlet case, and it worked in the Dirichlet case because of all this machinery that's going on under the hood, right? Okay. So now I think we have just enough time to finally see how this applies to the wave equation. Okay, so let's do that. So now let's consider the wave equation with homogeneous Dirichlet boundary conditions. So this is a 1D wave equation with homogeneous Dirichlet boundary conditions. Let's quickly write this, right? So this, the physical interpretation of this we thought of as a finite string with fixed ends, right? So finite string, the ends aren't moving, okay? And then we have an initial disturbance, right? So I have u sub tt is equal to c squared u sub xx. Okay, so here x is, again, somewhere on my finite string. T is positive. That's my PDE. My boundary conditions are homogeneous Dirichlet, so this is u of 0 of t equals u of L of t, which is 0. So if I think of u as being my position or my displacement, this is saying that the ends are fixed here. This is for t greater than or equal to 0. And then I have initial data. U of x0 is equal to phi of x. And so this is my initial displacement, and then I have initial velocity here. U sub t of x0 is c of x. And again, that's for x in on my string somewhere. Okay? All right. So separation of variables. Again, I seek u of xt, which is separated. So it looks like that. Now, what does this allow me to do here for this problem? So something's a little different here. We have two t derivatives instead. Okay, and so what does this yield? This yields the ODE expression x of x times t double prime of t is equal to c squared x double prime of x t of t. And just as before, we rewrite this as minus t double prime of t over, I'm going to put the c squared on the t, so this is c squared t of t is equal to minus x double prime of x over x of x. Okay. Just as before, we ask ourselves this question: what does this mean? I have a left-hand function only depends on, or I have a left-hand side only depends on t. I have a right-hand side only depends on x. According to this, if this has a hope of solving this PDE everywhere here, then this has to be true for all x and all t. And the only way that that can happen is if both of these are equal to a constant, right? So this must be a constant, must be independent of x and t. Let's again call this constant lambda. So this means that minus t double prime of t over c squared t of t is equal to lambda, which is equal to minus x double prime of x over x of x, where lambda is constant. Okay. And so I have two eigenvalue problems associated with the same eigenvalue, just like before. I get two eigenvalue problems. My two eigenvalue problems are as follows: x double prime plus lambda x equals 0, and t double prime plus lambda c squared t is equal to 0. Okay. Now, again, I have to impose my initial conditions here. And imposing my initial conditions of 0 here, just as before, if I want to get a non-trivial solution, i.e. if I don't want t to be identically 0 everywhere, the only way this can happen is if x of 0 and x of L are both 0. So again, I get Dirichlet. Right, my Dirichlet boundary conditions on the PDE descend to Dirichlet boundary conditions on my eigenvalue problem. And so I have two eigenvalue problems to solve as before. And the idea is that I solve this one first because I have canned solutions to this. This is actually the exact same that I had in all the other cases I've done so far for the Dirichlet case. And then here, once I found that eigenvalue, which I know immediately what it is, right? It's n squared pi squared over L squared for this problem. Then I use that particular eigenvalue to solve this, but this also is the same sort of eigenvalue problem, right? Okay, and so how does this work? Right, so let's do this one first. So solve this one first. Okay, so our solution is as before. I get eigenvalues. Well, let's consult our list. Well, let's see here. I want to solve this. Oh, that's exactly this thing on my list. And so I know exactly what my eigenvalues and what my eigenfunctions are. So my eigenvalues are lambda sub n, which is n pi over L all squared. My eigenfunctions x sub n of x is sine of n pi x over L. Right, there it is, an n some natural number. Okay, so n's 1, 2, 3, and so on. Now that I have these values for lambda, I plug these into my other ODE, t double prime plus lambda c squared t equals 0. Now I want to solve. So now I wish to solve the eigenvalue problem for t. Okay, which is t double prime plus lambda now is this thing, so it's n pi over L all squared times c squared t equals 0, right? But how do I solve this? Well, now I have an ODE, no boundary condition, so I don't even have to think about it as an eigenvalue problem. I can just think about this as I want the general solution to this ODE. So forget all the eigenvalue stuff that we did before, right? I just want to solve, so what is the general solution to this constant coefficient linear second order ODE, right? So you can think of characteristic polynomial if you want, or you can just say, well, I know that this quantity, this is definitely positive here. So I know the form that this has to take, right, is it's a sum of cosines and sines. And so the general solution from ODE theory is just C sub n cosine of n pi ct over L plus d sub n sine of n pi ct over L. Okay. And so now my step, thus my separated solutions for each n and n are given by u sub n of xt, which is x sub n of xt sub n of t, which is x sub n is here, t sub n is here, so this is going to be c sub n cosine of n pi ct over L plus d sub n sine of n pi ct over L times x sub n, which is sine of n pi x over L. So for each n, these are my separated solutions. And so I seek a solution that is just an infinite sum of these things. Right? Okay. And so how do I find these things? Well, so now as before, I consider the solution. Again, this is a linear constant coefficient second order PDE that we're solving. It satisfies the superposition principle, so any finite number, so any finite linear combination of these things is definitely going to be a solution that satisfies the boundary conditions. But now, I want to consider an infinite sum of these things that satisfies the initial condition. So far in my PDE, I've gotten something that solves the PDE, solves the boundary conditions, but the question of whether it solves the initial conditions is the part that I'm working on, right? So I want to impose the initial conditions now, just like I did before, right? Just like I did for the heat equation. So I consider the solution u of xt, which is the sum from n equals 1 to infinity of the u sub n of xt's, which is the sum from n equals 1 to infinity of just rewriting this thing. So I'm just copying this expression here. So this is c sub n cosine of n pi ct over L plus d sub n sine of n pi ct over L times sine of n pi x over L. Okay, and I consider the solution here, and I want to ask that it solves the initial conditions, right? So I want u of x0 equal to the specified phi of x, and u sub t of x0 equal to c of x. So let's impose the first initial condition first, right? So if phi of x is going to be equal to u of x0, plugging in t equals 0 here, I get, so plugging in t equals 0, what do I get? All those are 0. Right here I just get 1, and then I get c sub n times sine of n pi x over L. Right, so this is the sum from n equals 1 to infinity of c sub n, right? So this term goes away, this term is 1, so this is c sub n times sine of n pi x over L. This implies, so this will work if c sub n's are the Fourier sine coefficients, i.e. our usual, right? C sub n is the integral. These are Fourier sine coefficients of phi, I should say, right? Because this is phi of x. So this is 2 over L times the integral from 0 to L of phi of x sine of n pi x over L. So the second initial condition, right, is this one. And I can differentiate this thing term by term here. So derivative of cosine is minus sine with some constant, whatever, I don't care. And then this is derivative of sine is the constant, m pi c over L times cosine of m pi c over L here, right? And then I'm plugging in 0, so I am going to get a term here, right? So the other initial condition wants phi of x to be u sub t of x0. But this is saying that, again, when I differentiate this thing term by term here, so the t derivatives are only hitting the t terms. Here, cosine goes to minus sine, and when I plug in 0, that's going to 0, so I don't care. And then this one, sine becomes cosine, and the constant that multiplies it is n pi c over L. So this is, and when I plug in 0, cosine 0 is 1, so this becomes the sum from n equals 1 to infinity of n pi c over L d sub n sine of n pi x over L, right? Which is the Fourier, so this is going to be the Fourier sine series for phi with coefficient this n pi c over L d sub n. We could reindex this if we want to and divide later. So let's actually do that, right? So d sub n is going to be 2 over n pi c, right? So 2 divided by n pi c times the integral from 0 to L of c of x sine of n pi x over L dx. So in this last step right here, think of just relabeling this, right? If you're uncomfortable with this algebra, just relabel this. Call this like big A sub n, right? If you really like to relabel big A sub n, call it n pi c over L d sub n. And then you're just looking at the Fourier sine coefficients for A sub n would be the Fourier sine coefficients for c of x. find those in the normal way, right? Here they are. But then this is n pi c over L here. So multiply by L over n pi c, and you get 2 over n pi c times exactly what you want here. So this is exactly how to do that. So this is a mistake. This is just n pi c. Okay. And so my solution is of this form, where the coefficients c sub n and d sub n are essentially, well, so c sub n, it literally is the Fourier sine coefficients of phi. The d sub n are the like Fourier sine coefficients of c of x times some factor. Okay. All right. So I think that is enough for today. We'll investigate this. So now we have, I should clarify here that what we have done is we've solved this problem that seemed extremely intractable before, or very complicated, right? This fixed end finite string wave equation problem. We've now done this via separation of variables. And so tomorrow, like first thing in tomorrow's lecture, what I'll do is kind of go over a couple of consequences of this physically and what this solution actually tells us. Okay. All right, so that will be our starting point tomorrow. As I said, you'll have your next homework will be assigned soon, and it will cover separation of variables stuff. So you are going to get plenty of practice doing separation of variables in this homework, and then your last homework of the semester, which will be assigned next. So we'll say this coming homework might be due on like next Tuesday, and then the homework after that will be assigned on Tuesday and due on either Thursday or Friday, and then your final exam will be assigned next Friday. So not tomorrow, but next Friday. There will be time for you to do it within a couple hours on Friday, but I'll give you a couple days to do it. It'll be roughly the same format as the midterm. Okay. So anyway, that's the plans for the rest of the summer session. So anyway, I will see you all tomorrow.